Often we encounter with the terms like 32 bits OS or 64 bits OS. Actually, these are the addressing scheme of the operating systems. That means if an operating system is of 32 bits, then it's using 32 bits in order to keep address. Otherwise, if it is 64 bits, then the operating system is using 64 bits in order to keep an address. Now, with the 64 bits operating system, the operating system could manage 2 to the power 64 bytes of memory. That's the addressable space that the operating system can manage. And if it is 32 bits operating system, then the operating system can manage 2 to the power 32 bytes of memory. That is actually 4 GB of RAM. In order to understand this conception, let us take a fictitious operating system that is actually using 2 bits in order to keep address. That means the addressing scheme of the operating system is 2 bits. Now in 2 bits, only there could be 4 different values in binary. All the address and values all are kept in binary inside the computer, we know that. Now in 2 bits, there can be 4 different values in binary, 0, 0, 0, 1, 1, 0 and 1, 1. We cannot have any other value in 2 bits because only possible permutations between 0 and 1 in 2 bits are these 4. So there could be 2 to the power 2, that means 4 different arrangements between 0 and 1 in 2 bits. And this is actually 0 and this is 3. So the maximum value that we can have is 3. So if the address size of an operating system is of 2 bits, and we consider a fictitious operating system with 2 bits addressing scheme, then it can keep only 0, 0, 0, 1, 1, 0 and 1, 1. That means the addressable location could be only 4 because it cannot keep the address of more than this. So whatever the size of the RAM in that case is, only the 4 bytes, the 08 bytes, and then this is 0, 0, this is 0, 1 and this is 1, 0 and this is 1, 1. Only these first 4 bytes of the RAM could be addressed by this operating system using this addressing scheme. And in this case, the operating system cannot access the rest of the memory. Whatever the size of the RAM is, only the first 4 bytes could be addressed and used by the operating system if the addressing scheme is of 2 bits. So if the operating system is adopting addressing scheme of say 8 bits, then it is 2 to the power 8 bytes that is addressable by the operating system. So if the operating system is of n bits, then it is actually 2 to the power n bytes that the operating system can address. So if it is 32 bits operating system, then the addressable memory location is 2 to the power 32 bytes, that is 4 GB, 4 gigabyte. Otherwise, if it is 64 bits operating system, then the addressable memory location is 2 to the power 64. Now, whenever we declare a variable, say this particular computer is 64-bit Mac. So in my computer, if I declare a pointer or if I get the address of any variable, it's always 64 bits because I am using 64-bit addressing scheme operating system. So if you are using 32 bits operating system, then all the pointers are going to be of 32 bits because pointers are there to hold the address, and that is according to the addressing scheme of the operating system. If your operating system is of 16 bits, then all the pointers that you declare in your program will be of 16 bits, that means 2 bytes. So the size of the pointers is always fixed, and that is according to the addressing scheme of the operating system. If the addressing scheme is 64 bits, then the size of the pointer is always 64 bits, that is 8 bytes. If it is 32, then it is 32 bits, that is 4 bytes. So let me show you this. We can use the size of operator in order to get the size of a variable in memory. Okay, here we go. Let me take this example. Here I have declared 3 pointers, integer pointer, float pointer and double pointer. We can use the size of operator in C in order to get the size of a variable or type. So I'm just printing the size of each of these variables, pointer variables, and each of these is going to print actually 8 bytes in this case because I am using 64 bits Mac. So 64 bits Mac, that means 8 bytes, and therefore they are going to be all same 8 bytes because they are pointers, and pointers are having size according to the addressing scheme of the operating system. So you can see that they are all 8 bytes, 8, 8 and 8. Okay, now instead of this, if I just go ahead and print something like this, size of star P, star F and star D, then they are going to be different because star P is actually integer. Star P means we are dereferencing the address, and if we dereference integer pointer, that means we are going to get an integer. So that is the size of an integer. So here it is the size of float and here it is the size of double. So in this case it's going to be 4, size of float is 4 and size of double is 8. So you can see that it's 4, 4 and 8 in the second case. Now had we declared a character pointer, say here is character pointer k, and if we had printed the character pointer as well, the size of the character pointer as well here, and also the size of star k, then since the size of the character pointer, it's again going to be 8 bytes because the size of the character pointer is same with the size of double pointer and all others. But here star k indicates a character, so it's going to be 1 byte in the second case. So you can see that it's, I'm sorry, I have not given the format specifier here. It should be %lu because it's unsigned long. Size of always returns unsigned long. Okay, you can see that it's 1 byte here, but all the pointers are of same size 8 because I am using 64-bit MAC, and that's 8 bytes. So the pointers, the size of the pointers are exactly equal to the addressing scheme of the operating system. If your operating system is 32 bits, then size of the pointers, whatever the type that you use, it is always 4 bytes, 32 bits. If you are using 64 bits operating system, it's always 8 bytes, the size of the pointer. But the location that the pointer points to are different, obviously. They are according to the type. Thank you very much.